Welcome back to the programming language series where we're going to build a statically typed and JIT compiled language using nothing but Python and LLVM Lite. Today we're going to work on our compiler class and get that fully set up to handle our arithmetic code generation. Let's create a new file. Make that our compiler.py. Now in this compiler we're going to need a few imports, but before we can do any of that we need to install LLVM Lite. So this is part of the reason why I pushed for Miniconda at the beginning of this series, because all we'll need to do is a command conda install LLVM Lite. Now if it's not really working in the Visual Studio terminal, you may need to go to your search bar in Windows and type in Anaconda. There should be a little command prompt that you can open up and navigate to this directory and activate the environment and install this. So we'll conda install LLVM Lite here. And now that that's done, we're ready to get on with our imports. So from LLVM Lite, import IR. It's going to be the main object that we use today in this compiler class. And we need to import everything from our abstract syntax tree file as well. So I'm just going to copy and paste this. You could take it from the parser as well. Everything in here is matching with the parser besides this node type right here. So we just need to add that. So we'll get on with the compiler class. This class compiler, the constructor method, we do have a few things set up in here. We're going to have a type map, which is going to be a dictionary, key is a string, and the value will be an IR type, so an LLVM type. The only two things we are interested in right now is the integer type, so IR.int type, and this will be a 32-bit integer. And then we'll have the float type, which is an IR.float type. Next thing we're going to need is the module. This is going to be the main module, the main block, not block, but the main container for all of our code that we're generating. So self.module, let's type IR module. This IR.module. We'll name this module main. You can name it pretty much whatever, but main is what I'm going with. And then we'll need a builder. So self.builder. ir.ir builder, and then we'll call that function as well. Next thing is going to be the main method of our compiler class, which is just going to be called compile, and this is going to take in a node, and this is what is going to run recursively to walk down the abstract syntax tree. It's going to go from the expression statement, go in to the expression statement function. It's going to compile in here. It's going to visit the infix. It's going to visit another infix. Then it's going to visit an integer and resolve that value. So in here, self.compile. In this compile method, we're going to use a match case statement. So match node.type. This is where our function comes into play. First case we'll implement is node type.program. And this is just going to visit the program. Just a function to visit the program node. We'll pass in the node. Now down here we'll add another region block for visit methods. So we're just going to implement this visit program method. Def visit program self. It's going to take in a node, and that node is going to be a program node. So what we're going to need is the first off, for our language right now, we're not gonna, some languages need to have a main method. So in C you have the int main method. It's just the absolute execution starting point for the language. Right now we are going to fake it, just similar to how a lot of other languages do. We're going to create a main function and then put everything in our test file into that main function as if it was already there without us writing it. Later on, when we implement a little more, we're actually going to have to type the main method in our language, but for now this will do. So the first thing was need the function name. We're just going to name this function the main function. But remember what you name this, because we'll need it in the main.py file to actually call this later on. Need a param types list, which is a list of ir.type. So what are the parameter types for this function? It's going to be completely empty for right now. And the return type is an ir type. And we'll set that to our type map in the integer type. So we're going to return an integer from our main function. So we need the function type in the actual function block as well. So the fnty, so this is going to be our function type, is ir.function type. We have to put in our return type first. And then we're going to put in all of our param types. And then we'll have our actual function, or our ir function. First is our module, so self.module. Then we'll put in our function type. And then we'll put in our name equals func name. Name that func main. I need to name that func name. There we go. Now we need to define the function's block. So where is all of this code going to go into the function? So we'll name it block equals func.append basic block. And we'll name that block the func name underscore entry. Then we need to set the current builder for this function. So this will be scoped to whatever's in this function. So ir builder. And we'll put the block into the builder. Now the main portion where we're going to start being recursive with our compile function is here with our for loop. So for statement in node.statements, we're going to compile that statement. And at the end of this, we're going to set our return value. Just going to be a constant variable, or an IR constant. And this is where our self.typemap will be. It'll be a type of integer, and we'll make it the nicest number in the West. So self.builder.ret, so this is the return instruction. So we want to return from whatever function this builder is on. So we're going to generate that return instruction, and we'll just return this return value. We can move on to the beautiful expression statements. So in our compile match function, we're going to add a comment for statements. So every statement visitor method will go here. So case node type dot expression statement, and we'll do a self visit expression statement. We'll pass in the node, and we'll go ahead while we're here, just do the expressions block, and then we'll do a case node type dot infix expression self dot underscore underscore visit infix expression. We'll brag the node in there. First thing we'll do is expression statement though, and we're going to have a internal region block as well in here. So region, this will be statements. So this is all our visit methods for statements. So def visit expression statement. Taking a node which is of the type expression statement. Won't return anything. And all this will do is just, for now, compile the node.expression. Last visit method we'll need to implement is our infix expression. So we'll make another region block for that, for these expressions. So def visit infix expression self. Node is of course the infix. And none. We'll take the operator out of this node. We'll take the left. Now this is where we're going to have to implement another helper function to resolve a value from a node. So this function will return the value and the type. And then we call it resolve value. take in the node dot left node, and then we'll do the same for the right. So right type, self dot resolve value, and then we node dot right node. So we will go ahead and implement the resolve value real quick before we go to the rest of the functions. We'll go outside of this final end region and make a new region. Helper methods and region. And this is a really important function, resolve value. This is where everything's going to originate for doing our math, for resolving those integers, floats, strings, arrays, everything. So that'll take in an expression node and then a value type, and this will be used at a later date, but we'll just go ahead and put it in here now. This will return a tuple of an IR value object and an IR type object. We'll have a match statement based on the node's type. First case is node type dot integer literal. We'll go ahead and this is purely for IntelliSense. Equals node value type. We'll use capital T because lowercase is reserved by Python. First is going to be the node dot value, and then we'll do a little bit of one-liner if statements here. So type map. It'll be an integer type if value type is none, else value type. So this will always be none until we implement using this value type, where we're just going to set it up now. ir.constant, we'll just generate it and return a new ir constant with the type of type and the value of whatever value that is. And then the second part of the tuple will be the type. Same thing for the float literal. You can just copy paste this and copy paste the integer part, but change everything to just say float. Now the last part is the expression values. So there are cases where an expression will go into this resolve value function. And the only one we're going to care about right now is the infix expression, and that will just call our infix expression function as well. So back up to the infix, we'll finish this out. Set the value equal to none. We'll set the type equal to none. Now if is instance. This is a built-in function in Python just to check if one object is the same class or type of as another object. So we'll take the right type. If that right type is an integer type and is instance, left type is an integer type. We want to take this type equals self dot type map. This will be an integer. And then we're going to match again on the operator. So depending on which operator we use, we're going to emit a different instruction. So plus value equals self dot builder dot add, left value, right value. We'll add another for our minus sign. Value equals self dot builder dot sub, left value, right value. And then I'll copy and paste these other two here. So this is for multiply, just the mul function, and then slash for divide, sdiv. Now these functions are different for floats, so we'll implement that a little bit later. Just want to get the integers out so we can see this generated IR, and then we'll finish it. So we'll hang off on the modulus and the POW operators until the next episode, but this should get us through for right now. And then we will return the value and type from this function. Now from right here, we can actually go to the main.py file. From compiler, import compiler. And there's a few weird imports that we're going to have to do. So from LLVM Lite, we're going to import IR. From import LLVM Lite.binding as LLVM. And then we're going to have to use the ctypes module. Ctypes. Import cfunc type. And we're going to take a C integer and a C float. We will not use these yet, but when we're executing, we will use these C types. So moving down, we're going to grab this program and take it out of here. We're going to put it above this. We're going to check if the length of the parser.errors is greater than 0. We'll just print them to the screen. p.errors. We'll print the error, and then we'll just exit out of this program with a code of 1 for now. Why not? Next thing, we're going to set up our compiler class. Get an instance of that. We're going to hit the compile function, node.program, or node equals program. Now these are our output steps for now. We're going to take the module, which is an IR module, the c.module, which is our compiler. We're going to set the triple. So this is basically our target architecture. This is just going to get the default triple from whatever operating system you're using. And I'll show you where this is in the IR. We'll go up, we'll add a compiler debug flag equals true. We'll set this to false for now. And then we'll come down here and we'll check that. So if compiler debug, we're just gonna with open debug /ir.ll, then as f, we're gonna do an f.write, and we're just gonna stringify the module that we got up here. Alright, so this should all that we need. We need to, I guess we can create a compiler.lime. You can still use one of these if you want, but we'll implement 5 + 5 with a semicolon. And we will run python main.py and see if we can do it now. Alright, so ir.ll has been made. So this is the LLVM intermediate representation code. So we have our module. This is where we named our module main. This is the target triple. I'm on a 64-bit PC that's a Windows. So that is my target triple. It just automatically grabbed that. This data layout we can take care of later. It doesn't really matter for right now. This is the main function that we created from scratch inside of the code, and that we just injected the rest of ours. So this is where we return an i32, which is an int, 32-bit. The name of that function is main. The first block in that function is the main entry block. This is where we add, we can take the compiler right here. So this is where we add, the first instruction is our add instruction. It's an integer add, 5 + 5, and that will go into this variable. And then I guess we forgot to set the compiler test, so I think it just used the parser. Yeah, it did. Alright, so use the parser. Where's my IR? Alright, now we're here. So it uses the parser file, so that's okay. It's a little better. So the next thing is this 0.3. It multiplies the result of this 0.2, which is 5 + 5. And then it multiplies that by 10. And then that's where we can get whatever this is, that's the value is stored here. We don't have a way to see it yet. And then we have our return nice number, beautiful number down here. And that is the IR code. So this gets a lot more complicated, a lot more complex, but there's no need to get that far into it yet. We will take this step by step. But that's the end of episode 3. In the next episode, we're going to implement the rest of our arithmetic operators. So thank you for watching. Discord is in the description if you have any suggestions or any features you want to see added to this. Please leave that in the comment section as well. I will see you guys in the next episode.